Hello again. So the complex fraction one finishes out the three main algebraic techniques we use when we get a problematic 0/0 situation. Later on, we'll have a calculus technique we can use for these kind of crazy limits that would make some of these problems a lot easier to work with, but there is some value in doing this algebra because you do have to do this kind of stuff for some of the weird integrals in Calc 2. So you can try factoring, rationalizing if you have a weird square root, or if you have little fractions and big fractions, simplify it so there's no little fractions. All right. The next one we have actually shows up on your new writing assignment. So it's called the squeeze theorem. So I've got this upper pink graph and this lower blue graph, and we want to ask ourselves, like, can I put graphs in between those two? Like, how many different graphs can I put between the pink and the blue? Like, they always stay below the pink, they always stay above the blue. Now, when we say graphs, like, we're really thinking functions. So don't like go scribbling back on itself, but you know, I could have a function that's like, I'm gonna go here. Oh, nope, now I gotta go back up. Oh, gotta go back down. Hey, why are you guys getting so close up? And there they go. I could have a different graph that's like, I'm gonna go down here. And oh no, that's coming up. Oh no, oh no, oh no. I have to bounce. I don't want, fine. So all these graphs are gonna be forced through that point. Now I know in the original picture it didn't look like they touched there, but the whole point of the squeeze theorem is that whatever we pick for our top and our bottom function, they actually meet at the point where we think the graph that's weird to evaluate goes through as well. So that's the idea on the squeeze theorem is, what if I have this weird oscillating crazy trig thing in there that it looks like it's going to this point, but I can't say for sure just based on plugging in. So this is a way to categorically say, nope, this graph above it will shrink in on that point. This graph always below it will shrink in on that point. So the two of them will squeeze, or I think of it like sandwich, and force it to go through that point, or more, prove to you that it must go through that point. So here's our more formal definition. Let f, g, and h be defined for all x not equal to a over an open interval containing a. If f of x is less than or equal to g of x, which is less than or equal to h of x, for everything except the value in question, and we know the limit as x approaches a of f and the limit as x approaches a of h equal L, the same thing, then they force g of x to also have that same limit. So none of these functions have to be defined at the value a, but we need them to be defined at all the values really, really close on either side of a. So when we use the squeeze theorem, we start with the g of x. Had a student ask me that in the tutoring lab, and I was like, that's a good point. It's not very clear from the setup. But we have some funky function that we're like, putting the thing in ain't gonna do the do. But I do know other things about this. And so this is the very, very common setup that I somehow lost all the extra space I put in here. All right. So the limit of x squared times sine of 1 over x. So with every limit, the first thing you do is plug in the 0 and see what happens. Like 0, because that's the value we're approaching. So we have the limit of is 0 squared times the sine of 1 over 0. So 0 squared is 0. That's fine. But the sine of 1 over 0, like we haven't even talked about what 1 over 0 does. And in fact, if you look at the graph of 1 over x, on either side of 0, it actually goes to positive infinity or negative infinity. So it's this weird, like, what's it gonna do? But that x squared in front is giving us a key that this is not going to just be a funky, like if you look at the graph of sine of 1 over x, it's horrible. There is no limit as x approaches 0 there because it constantly pings back and forth. But every sine graph, just sine of a thing, is bounded above and below. So if you think about your sine graph from pre-cal, it goes up, hits a value, goes down, hits a value, up, hits the same, down, hits the same. It always oscillates between +1 and -1. So I'm going to start with my sine of 1 over x. That's like my real problem here. And I know for sure that will always be less than or equal to -1, or rather, -1 and +1 are always below or above it. All right, but that's not what's in the limit. The limit has that x squared, correct? So what we're going to do is we're going to multiply by the x squared. If x squared was 0, it will make everything 0. They'll still be equal. The inequality is still true. If x is any other number, it gets squared. It's positive. Multiplying by a positive number doesn't do any weird flippy the inequality. So it's fair game to multiply everything by x squared. So I'm just going to write it underneath because I didn't really leave myself room. Then I'll write it down here. So now we have x squared sine of 1 over x is less than or equal to -1 times x squared. So that's not -1 in place of the x. That is -1 as the coefficient of x squared. And then on the other side, we will have +1 times x squared, which you can just write x squared, but just for, both sides look at the same. So I know for sure that's the case. Now, -1x squared and +1x squared, those are functions I can evaluate on any value because you just plug it in and see what you get. So we go back to the original problem. This was looking at the limit as x approaches 0. Okay. So that's what we're going to do. We're going to evaluate the limit as x approaches 0 of both of the outside guys. And when they both go to the same value, it's going to force our ugly guy in the middle to go to the same place. Which 0 squared is 0 times the number, still 0. And then same song, second verse over here. And ready. So since the thing that is always below our graph goes to 0, the thing that is always above our graph goes to 0, they're going to close in, sandwich, and say, boom, you're going through 0 as well because we said so. So this is where in like fancy math terms, we'd say, therefore, by the squeeze theorem, I hate writing out the word theorem, so you're getting THM. The limit as x approaches 0 of x squared times sine of 1 over x must be equal to 0. And then some people put this little box and you shade it in. And that's the like more formally math symbol of thus it is proved. I have done the thing. Or proof over with. Sometimes people will put QED. It's a stupid Latin phrase. I say stupid because it sounds pretentious, but old school mathematicians really loved sounding pretentious. All right. So another thing we can prove with the squeeze theorem is this little limit down here at the bottom. Like we get for free that sine of theta as theta goes to 0 is 0. Like you look at the graph, that's what the graph do, so that's what the limit does. The same thing for cosine of theta. In fact, sine and cosine are continuous everywhere, so we can just plug the numbers in. We don't have to worry about left hand, right hand, not agreeing kind of stuff. But that's one of those, like, we technically should prove they're continuous before we make use of that fact, but we kind of make use of the fact beforehand just to make it make more sense to y'all, hopefully. But sine theta over theta, we are going to see that show up in a whole bunch of weird trigonometric limits. So when I plug theta in for 0, the sine of 0 is 0. When I plug 0 in for theta on the bottom, it's 0. So I have a 0 over 0 indeterminate form. But I know I can bound my sign by -1 and 1. And my brain is like, but if I put 1 over x as it goes to 0, it's confusing. I don't remember the details, so I'm not going to go over the details, and I'm not going to expect you guys to know the details. But I am going to want you guys to be able to utilize that result. And that's what we're going to do in the next several questions on the next video.